Hello students, welcome to week 6. So we are moving to the next unit in this week. We are going to move from our analysis on transmission lines to considering electric and magnetic fields in the most general form in three-dimensional space. We notice that whatever we have equipped ourselves with so far is mostly restricted to situations where there are conductors and I can actually define something called voltages and currents, especially in high frequency circuits. So there are also applications where, for example, in your cellular communication, we have microwave radiations going to and fro from the base station to your mobile phones. Now these microwave radiations are essentially traveling in free space, right? There is little to talk about in terms of voltages and currents while the microwave is propagating in free space, right? So when we look at electric and magnetic fields in purely dielectric media or in free space propagation, voltages and currents are perhaps not relevant. And as I mentioned earlier in this course, the reason to focus on voltages and currents is one, we reduce the complexity, the number of dimensions to only one spatial dimension, and then we have the time axis. Over here we are going to now start looking at electric and magnetic fields that's pervading in all of the three spatial dimensions and time. But before we can dive into looking at electric and magnetic fields specifically, it is customary to educate ourselves in the mathematics that is required in order to make the sense out of the results that come from solving the Maxwell's equations, right? So this week is going to focus mostly on trying to give the background mathematics that is necessary in order to appreciate the works that we are going to do later on in this course. So we are going to start with the idea of scalar and vector fields. Remember in the introductory lecture itself, I introduced the idea or concept of fields, and among fields we actually have two different kinds. Okay, so one is the scalar field. The best way to understand both scalar and vector fields is through examples, right? So scalar fields essentially, you can think of every position in space x comma y comma z. I can associate a particular scalar value, that is a singular number, to every location in space. This is a scalar field. One example can be the temperature map. Okay, it could be the temperature map around you, it could be the temperature map over an entire city, or maybe even across cities in a country, right? So every location x comma y comma z, I can associate a particular local temperature. A second example is the elevation map. Right, so we are associating the height or altitude of different points in some geographic location, right? So these two are examples of scalar fields. Okay, so you can think of associating temperature at x comma y comma z, and elevation map indicates say height h at locations x comma y, right? So the value of t x comma y comma z for any point is a scalar. That's why the name scalar field. And elevation maps, if you perhaps go into Google Maps, and maybe select the terrain, right, you might find something like these. These are essentially contours indicating the same elevation, right, and the number that is written on each of these contour lines indicate the elevation, say in meters or feet, whatever it be. Now this is essentially a representation of your elevation map, right. So for every location, geographic location x comma y, I can associate a certain altitude, right. So for example, this could be an example of an elevation map for say a very small hill, right. Now on the other hand, vector fields, I now associate 3 numbers for every location x comma y comma z, right. So examples can be, say, the air velocity, right. So if I were to go to a very specific region in the space around me and locally measured the air velocity, I would not only get the speed of the molecules that would indicate the magnitude, but also the wind might be oriented, right. The local motion of molecules could be in a certain direction, right. So there is both a magnitude and a direction specified at every location x comma y comma z, right. So I would need such a database in order to represent the behavior of the molecules in the air, right, around me. One can also think of fluid flow, right. So airflow or fluid flow is a very common example cited for vector fields. Even in other lectures, you might find most people who take up the responsibility to introduce vector fields try to use fluid flow or air flow. This is very convenient in order to picture something in our minds, right? But I would like to caution you that in the case of electric and magnetic fields, which would fall under the category of vector fields, where every location I would have a certain magnitude for the electric field strength and a direction in which it is oriented, right. But in the case of electric and magnetic fields, there is really no fluid, right, or there is no motion of anything, right. So going back to the analogy in transmission lines, it is only an apparent motion that we tend to see, right. So electric and magnetic fields are but the representation wherein I would require both the specification of a magnitude and a direction for every point in space, okay. Okay, we need to specify both magnitude and direction for each location in space. Now, in order to represent the magnitude and direction, we would again require 3 variables, okay. So now we have to come up with certain basic rules so that we can all agree upon these common rules and we can represent the electric and magnetic fields using these common rules, right. So the first thing that we will need to agree upon is the coordinate systems, right. So based on the symmetry of the problem, there may be specific coordinate systems that might lend us to solve the problem more elegantly. So we largely have 3 main coordinate systems. So in 3 dimensions I would require 3 independent scalars, right, to represent any location in space. Now the question is, what do these A, B, C represent in each of the coordinate systems? The most popular so in the rectangular coordinate system, we essentially divide our instruction to get to a specific point in 3 dimensions, where we identify axes x, y and z, and say I would like to get to a point A, comma B, comma C. The ordering of A, B, C in this ordered triplet is important, right? So we have a point that we call the origin. Okay, the instruction would be to follow this path, which would be move A units in x and then move B units along, or let's say parallel to the y axis, and finally move C units parallel to the z axis, right? So you can think of the Cartesian coordinate system as essentially giving instructions to walk in straight lines, right? And that I start from the origin and I essentially execute 3 instructions, right? Now I said the ordered triplet of numbers, the ordering is important, right? And also the orientations of x, y and z in the 3-dimensional space is also important, right? So we say that the x, y and z axes follow the right hand thumb rule, which is if I were to use the 4 fingers to go from x to y, the thumb indicates the direction for z, right? So if I were to take any of these in order, that is, if x and y were to be represented by the movement of my 4 fingers, then z would be the resultant, which is indicated by the thumb, right? And similarly, if you took y and z, I would get the direction of x, and z and x, I should get the direction of y, right? So this is true in general for all the coordinate systems that we are going to see. Is the 3 coordinates, the ordering is very important, right? And they also obey the right hand thumb rule. Okay, so the next triplet is in the cylindrical coordinate system. Here the instructions are slightly different. Okay, so let's say I'm looking at the same point in space physically, but now I have a different set of numbers A, B, and C in the cylindrical system, where the instructions are again I have an origin here, right? So I move radially out by A units. Okay, and then I follow the path along the arc that I've shown, right? So all the points on this arc are equidistant from the origin, right? So I'm following along the circle for B units, and then I'm going up in elevation by C units, right? So move along the circle of radius A by B radians, right? So B is actually a measure in angle, right? And 3 move parallel to Z by C units. Okay, so this is our instructions for the cylindrical coordinate system. So here similarly, if I look at the point ABC, the radial component is looking away from the vertical axis, right? And then you have the phi direction for the angle, right? So we can say this is R, phi, and we have Z, right? So you can also see that R, phi, and Z in this order. These directions again follow the right hand thumb rule, right? So the order is R, then followed by the angle phi, and then the height Z, right? Finally, we have the spherical coordinate system. Okay, so I am now again looking at the same point ABC, but the instructions and what these ABC mean are now different. So first I move out radially from the origin, and then I descend and then finally I move along the sphere, right? So you can think of B and C are essentially latitudes and longitudes, right? That is perhaps the easiest way to picture spherical coordinate system, right? So for any location on Earth, we just use the latitude and longitude because the radius of Earth is more or less fixed or constant. So we are just on the surface of the Earth, but in spherical coordinates, you can essentially dictate how big the sphere is, right, by the first coordinate A, and then moving along the sphere of A units, radius of A units, you can talk about longitudes and latitudes, right? So this is the second. So that is your theta, that is your latitude, right? So you specify the radius first, A units, and then you have the latitude, which is the angle from the North Pole, right? And then you have the longitude, right, which is the phi. So usually you can represent this as r, theta and phi. So I now am using one distance measure and two angular measures to specify the same location, right? Okay. So in this case, you can notice that the directions for your r, theta and phi so r is always radially outward from the core, right? So or the origin point. So let's call this the origin. So we have r radially outward, and then the theta axis is essentially pointing tangentially but down. Then we have the phi axis, similar like in the cylindrical coordinate system, would be along the latitude line, right? So again you can see the ordered triplet r, theta and phi follow the right hand thumb rule. R and theta, when I keep my fingers going from r to theta, the direction of phi is given by my thumb, right? So you can notice that for the cylindrical and spherical coordinate system, that are the so-called unit vectors, right? So each of these arrows that I have drawn are actually unit vectors in each of these coordinate systems, right? And these unit vectors, actually their orientation or direction is changing for every point, right, in the case of cylindrical and spherical. Whereas in the Cartesian or rectangular coordinate system, the unit vectors just translate, but they do not quite change in direction, right? So it's perhaps the one difference between rectangular coordinate systems and the other two. Okay, that as I keep going to different locations in space in cylindrical and spherical coordinate system, I notice that the unit vectors locally at that point can keep changing its orientation, right? So for a different latitude longitude point, I can expect the r theta phi to actually be different set of vectors, right, looking or pointing at different directions.